All right. So we're doing inverse functions and relations, and I'll start with relations. Relations is like the big descriptor. Functions are special kinds of relations. So let's talk about inverse relations first and write down this definition. Two relations, and a relation, when I say relation, I'm just saying a set of ordered pairs. Okay? Two relations are inverses if one relation contains this ordered pair, A comma B, and the other contains B, A. Okay, so if they are inverses, one contains AB and the other contains BA. So let me give you a relation, a set of ordered pairs here to write down for an example. I got -8, -3, -8, -6, and -3, -6. There's my relation. The inverse of that relation, anybody want to take a shot at it? What's the inverse of that relation? The original. Michael?
Oh, it's just like
It is exactly just like that.
you want to put the sign too?
No.
-0.
Okay. Keep going.
Oh, -6, -8.
All right.
-6.
Okay. Any questions on what the inverse is? Just switching the x and y coordinates around. So, let's go ahead and graph this relation. -8, -3, -8, -6, 4, 5, 6, and -3, -6. Okay, I'm gonna go ahead and say like it's vertices of a triangle. So I'm going to draw a triangle here. These vertices. All right. In green, let's graph the inverse. -3, -8, -6, -8, -6, -3. And I'll connect those. And then I'm also going to graph the line y equals x. Y equals x. So like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and so on. Yeah, I got a little crooked there. And I'm going to go through here. Okay, so there's the line y equals x. Everybody know just how to split the first and third quadrants right in half along the diagonal? Graph y equals x. So I want to see what you might notice about that. I'm going to kind of color in this red triangle here. I'll color in the green one a little bit. You don't have to color these in. I'm just doing it for effect here. What do you notice about the two triangles in relation to y equals x? Go ahead, Tyler.
The diagonal meets like right where the edges of the triangles meet.
Yes. So you're talking about like here?
Yeah.
Where those triangles meet is also where this diagonal, this y equals x line goes through. That is a very good observation. It only goes through those points of intersection there, right? All right, as far as the graphs are concerned. All right, I also would like for you to notice, like this point here and this point here. What do you notice there?
They're like equally apart from the center.
You're right, from the center being y equals x. How about this point and this point? You feel like the same way? How about these points and these points? So I could almost reflect this point to here, this point to here, and this point to here. They are reflections of each other? Okay. So let's write that down. A relation and its inverse reflect over y equals x. All right? So far, so good? Now, let's go into the properties of inverses a little bit. Okay, now we're talking about inverse functions. And functions are special kinds of relations. But the inverse, and this is a notation thing, the inverse of f of x is written this way. F and then that negative 1 power kind of x. And it's literally the inverse function of x. So when you see this function of x, you see this, you say this. Okay? Now, if f of a is equal to b, then the inverse function of b, is equal to what? It is. Okay, and that's for all a's and b's, for function and inverse function. Now, for example, and I'm going to give you an example of a function and an inverse function, then this actually works. F of x equals x plus 4. The inverse function of this function is equal to x minus 4. It doesn't work that you can just change the signs on all these. That's not how it works. But this is one case that is true, and we'll show you here in a second. So, what's f of 7 here? You take 7 plus 4, which is 11. All right. Let's then take the inverse function of 11. What would we do here? 11. Inverse function of 11. Natalie? Oh, sorry. Okay. 11 minus 4. And what is that? Equal. What's 11 minus 4? Somebody say it. 7. Thank you, Michael. So, this function has 711 in it. This function, the inverse function, has 117 in it. See how it's just flipped around, the x and y coordinates? All good there? All right, well then next, let's go into what one-to-one functions. And definition, a function is one-to-one if its inverse is a function. Okay? And I want to look at an example here. So let's say f of x is equal to x cubed. I'm just going to make a quick sketch of f of x. It kind of goes through the origin like this and then comes back up like this. That's what f of x equals x cubed looks close to. Do you remember the vertical line test when you were testing for functions? What does it kind of say, Jack?
If you have one vertical line,
What will the vertical line or any vertical line do?
it would make the equation no solution, right?
Not quite. I think you're thinking of something else there. Just if I draw any vertical line, how many times am I going to hit this function?
Just once.
You're going to hit it exactly once. Right. If you hit it at all. No more than once. Okay. So vertical line test shows that f of x equals x cubed is a function. All right? We also have, for this helps with one-to-one, we have a horizontal line test. And that shows that, okay, well, first of all, let's do the horizontal line test. Let me do that in green. Does it pass the horizontal line test? Okay, it does. Shows that the inverse function of x is also a function. So not only is f of x a function, its inverse is a function. When that is the case, this means that f of x equaling x cubed is a one-to-one function. Okay? Let's just look at another example. Let's look at f of x equals x squared. F of x equals x squared. Remember how that looks, what the graph of that looks like? The parent function for quadratics, what's that look like? Remember? A parabola. This is a quadratic, right? All right. Let's just abbreviate here a little bit. VLT for vertical line test. Does it pass? It passes the vertical line test. Yes. That means f of x equals x squared is a function. All right? Horizontal line test. Does it pass that? Michael? No. Look, this horizontal line is going to hit it twice. Any horizontal line that hits it twice means that it doesn't pass. So, no, it does not pass. So its inverse is not a function. The inverse of f of x equals x squared is not a function. So this is not one-to-one. Just by the graphs, are you seeing that this one is one-to-one and this one is not one-to-one? Okay. Going to turn the page just to get started, and then I'll pause it here. We are finding and graphing inverse functions. I'm going to start with a function here.
Oh, that's a good laugh.
So we're going to find the inverse function of f of x equals 2x plus 4. We're also going to graph the function and its inverse when we're done, and just notice anything. But it's a step-by-step process that we're going to write down here. So step 1, whenever we're doing this, we're going to replace f of x with y. That makes y equals 2x minus 4. Okay, now step 2. We're going to switch x and y in the equation. So, what's that look like? That's going to look like x equals 2y minus 4. All right. Step 3, we're going to solve this equation. We're going to solve for y. I'm going to rewrite it. X equals 2y minus 4. And I'm solving for y, so I'll add 4 to both sides. And I have x plus 4 is equal to 2y. And I'll divide by 2 here. And I have x plus 4 over 2 equals y, which I'm going to put the y first. Y equals x plus 4 over 2. Step 4. Let's go back and replace the y now with function notation. But we'll replace, because it's the inverse of f, we'll replace y with the inverse function of x. All right, so that will be inverse function of x is equal to x plus 4 over 2. All right, so here's my function, f of x equals 2x minus 4. Here's the inverse. The inverse function of x is x plus 4 over 2. Is everybody okay with that? Now, I said let's graph both those. And let's graph f of x equals 2x minus 4. It's y equals 2x minus 4 is the other way of thinking of it. What's the y-intercept for that? Michael?
-4.
-4. So 1, 2, 3, 4. Let's put a point at 0, -4. What's the slope? Two. And I'll write the fraction 2 over 1 so that we can go up to rise over run. Let's fill our grid up with that. All right, and down to left one. And draw. Okay. So there is f of x. Now I'm going to draw the inverse. I'm going to use green for the inverse. And I'm going to rewrite it also. I'm going to write x over 2 plus 4 over 2. And a way of writing x over 2 is the same as 1/2 x. And 4 divided by 2 is 2. So I'm just... So now I know that the y-intercept is 2, correct? The slope is 1/2. So I go up 1 over 2, up 1 over 2. This is doing what you were talking about before. It's hitting the line. Up 1 over 2. Down 1 over 2. One more. Okay. Now I'm going to draw that line. And I'm also going to graph in this just to see what it looks like. Graph y equals x. So let's put that in there as well. So before I forget, let's make sure I designate that this is the inverse function of x in green. Red's got the... And then in red again, I'm going to graph y equals x. Remember 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. It's going through that point of intersection. Goes through there, doesn't it? And then I'll do it over here. What are you noticing about the two lines and relative to the line y equals x? What are you noticing about that? Michael? Equally split. In fact, I think we could say that we could reflect one line over that other line, right? So, and in general, we say this. The graphs of functions and their inverses reflect over y equals x.